I'm Fred Schreider, Senior Director of InterDigital's Wireless Labs, and today I'll be showing you some of the exciting technologies that we've developed for our European and US testbeds. So InterDigital for the last few years has been developing cutting-edge wireless platforms to be used by advanced researchers throughout the world. In the US, with the US Ignite Power project, we're involved with some of the testbeds that are focusing on millimeter wave technologies. So what I will be showing you today are two demos. One of them is running live in our New York lab. This is our 28 gigahertz millimeter wave 5G NR physical layer design. It includes a base station that you see here on the left and a terminal device, or UE, on the right. The terminal is on a tripod which is moving very slowly in order to demonstrate the NR beamforming capability of this platform. So the platform is streaming live KPIs from the base station and from the UE through this web server, and over here that you see is the web application, which I'll describe in a few minutes. So I'm just going to play a short video which will demonstrate what's happening in the lab. As you can see, the UE is turning at approximately 7 degrees per second, and it sweeps over a 90-degree sweep. If I pop into the web interface here, it shows you what's going on inside of the receiver of the terminal or the unit on the right-hand side. So here we have the beams being managed at the UE, and as the beam is rotating, you can see that the beam index of the UE is changing while the beam index of the G node B is staying constant. So this is showing what's happening with millimeter wave and NR, where they've added the capability of steering beams to the individual users. So the beam that's highlighted in blue here is the beam that is actually active at the moment, and as you see, it's changing throughout the sweep. Down here is the spectrum plot of the downlink shared channel, which is being received by the UE. It's 200 megahertz wide, which is one of the, I'd say, the promising features of the millimeter wave NR is its wide bandwidth. And we're running on a QPSK modulation, which is shown here in this graph. And this is the physical layer throughput up here, which is somewhere in the neighborhood of around 200 megabits per second. What I also would like to show you is what's happening on the base station side. So if I move over to here to this tab, now we'll see what's happening. KPIs are being captured off of the base station. So because this is a demo that we're showing one direction, here is a control channel from the base station being received that's being sent by the UE. It's a narrowband signal. It has control information on how to set up the channels of the physical layer in the UE. And we can see that there's very little data here because it's a control channel. It's about a little over a megabit of data. Again, here is the constellation, which is important to show what modulation is being run over this channel. So likewise, on the base station, you'll see that a single beam is being sent to the UE. So this is beam number 3, which is always being fixed on the base station, and it's indicated right here. And over on this side is what the UE is receiving, is what I showed you on the previous screen. So the intention of this application that I've shown you is to be used by the testbeds, as I mentioned at the top, for the US and for European 5G testbeds. So we built a utility tool as well as the hardware. We have our modem, which we call our MPU, modem processing unit, and this is a 28 gigahertz phased array antenna. The antenna is outdoor worthy, so this can be deployed in an outdoor testbed, and the modem unit will typically stay indoors. I'd like to show you one other key part of this demo, which is our Ldpc decoder, which is running on a GPU. We're taking the modem, which you saw in the MPU box here, which is an FPGA-based implementation, and we're moving it into a GPU. So this would be a software-defined radio when we completely port the FPGA code into a GPU. Now, the GPUs are much cheaper, and they're becoming very, very widespread use in artificial intelligence and machine learning. and it has a lot of promise for modems, which typically were done in ASICs and FPGAs. But the speed of the GPUs have increased so substantially that these things can actually be tried to be done inside of GPUs. So one of the most signal processing intensive functions in the modem is what they call Ldpc decoding and encoding. So the Ldpc decoding function has been ported already into the GPU, and I'd like to demonstrate some of that to you now. So what I will do here is just set some of the parameters of the encoding. For 3GPP NR, there's base graph 1 and base graph 2 and different ZC sizes. And what this does is create a very large matrix that has to be solved for. And this is really a perfect application for a general GPU. So I'm going to set the base graph 2 to 176 ZC. I'm going to be running about 1,000 packets through here, and we'll encode this in real time on the GPU. It should take a few seconds, and now here's the result. So what this is showing is that we can encode a code word in 2.64 microseconds. And the parity checked out to be 0, which is good. All the encoding passed. So now that we've got this encoding process done, we will now do a decoding, which is the more signal processing intensive part. So I have two ways of doing that here in this GUI. One is I could set a specific SNR, signal to noise ratio level, and let the processor do its job. The second one, I do the same thing, except I can set a sweep. So I can set a minimum SNR and then a maximum SNR, and have the GPU calculate and calculate the block error rate that's as a result of the SNR. So in this particular case, I'm going to show that the SNR is pretty low. It's a low SNR, and when I run the decoder, you'll see that it took a mean number of iterations. That's how many times it had to crunch away. The minimum is 8. The max number of iterations is 16, and the mean turns out to be 11.6. And this is very important because you don't want to have to wait to many iterations in order to decode, because this is taking up latency. So what we're showing right now is that the total latency to do this processing was about 900 microseconds, which is a pretty good reasonable estimate for a low bandwidth application. If I then come over here, I can actually do a sweep of the SNR. I could set a minimum SNR. I'll change this to -4, which is what I had set there. And then I'll set the maximum SNR to 0. And I'll run the decoder sweep, and this will be incrementing every 0.25 dB. It's actually running off our server right now. It's going to take a few seconds. So the result is in, and this shows that we've encoded a base graph 2, ZC of 176. We sent 1,000 packets. The maximum durations were set at 20. The SNR sweep from -4 to 0 dB. And you'll see that we've got a block error rate of 10 to the -3, 10 to the -4, and then 0. So between -4 dB SNR and -3.5, we went from a small block error rate to no block errors. And this actually is very significant, because it shows that we can actually encode this, decode this Ldpc in real time and get a very good result.